Hi, I'm Ms. Wong. Let's look at differentiation with negative indices. Does this rule apply for negative indices? This rule over here, where we bring the power down and then subtract 1 from the power? Well, we can test out using first principles, the most basic one, which is x to the negative 1, or in other words, 1 over x, and see if it follows the pattern. So let's do first principles. It's going to be a bit of a pain. I probably dislike this as much as you do. So 1 over x for x plus h would be 1 over x plus h, and then minus f of x is just 1 over x, dividing by h. This is fractions, so we have to find a common denominator. So we do that by multiplying the left by x and multiplying the right by x plus h. Dividing by h means multiplying by 1 over h. So now we can join this together because they have a common denominator. So x minus all of that over x plus h. Then don't lose your times 1 over h. Now x minus x is nothing, and then minus times the h is minus h. Now we can cancel out the h's, and we're left with minus 1 over x squared plus xh. And when we apply the limit, h approaching 0, so sub h is 0 into there, we are just left with minus 1 over x squared. And minus 1 over x squared can be written as, bringing the x squared to the top, x minus 2. So minus x minus 2. So our original function, 1 over x, I can write that as x minus 1. And let's see if it follows the pattern. So x minus 1, we're hoping that becomes that. So bringing the minus to the front is minus x. Then minus 1 minus 1 from the power is minus 2. So it is the same. So this pattern also works for negative indices. Be very careful with your negatives. Okay, let's do example 1. So by first principle, let's derive this. So we're going to use that pattern. So wherever you see x, we're going to do x plus h first. So the limit of all of that where x is x plus h minus all of that, and then dividing by h. So again, to combine this, it's fractions, so we have to find the common denominator, and we do that by multiplying the left by the right denominator and the right fraction by the left denominator. So we have this at the top here minus that. And don't forget, dividing by h means multiplying by 1 over h. And now we can cancel a few things before we have to write all of this over again. So the x minus x disappears, and the minus 2 minus minus 2, which is plus 2, also disappears, and we're left with minus h. And then we have to expand this. So x times x is x squared, x times h is xh, x minus 2 times minus 2 is minus 2x, and then we expand the minus 2 times all of that becomes all of that over there. And then don't forget the times 1 over h. The h can cancel out, and we're going to apply the limit so we can stop rewriting all this all the time. So when h equals 0, we can see that that goes and that goes. So now we're left with minus 1 over x squared minus 4x plus 4. So that is our derivative by first principles. You can also factorize it and write it like so. And you can bring that up as well. Now we're going to do another example. Differentiate each of the following using the rule, which is going to be so much faster. So here we have that where x is not equal to 0, because if x equals to 0, then the denominators of these two will be 0, and that wouldn't work. So differentiating, that means 3 times 3 is 9, take away 1 is x squared. Minus 2 times minus 2 is positive 4. Minus 2 take away 1 is minus 3. 5 times minus 1 is minus 5. Minus 1 is minus 2. And then a number by itself disappears. Let's try another one. So minus 4 times 5 is minus 20. Minus 4 minus 1 is minus 5. 7 times 3 is 21, minus 3 minus 1 is 2. Minus 2 times minus 2 is 4. Minus 2 minus 1 is minus 3. 3x just becomes 3, and the 8 disappears. Okay, find the gradient of the tangent to the curve determined by the function blah 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 at the point 1, 0. So what are we looking for? We're looking for the gradient at 1. So I'm going to write gradient at 1, so now I know what I'm looking for. So let's derive it and then find when x is 1, what is the gradient equal to. So first derive it. I'm going to write 1 over x as x minus 1. So that makes it easier for me. So I'll bring the minus 1 to the front, and the minus 1 is minus 2, and then minus x squared becomes minus 2x, and 2 minus 1 is just 1. So now letting x equal 0 and finding the gradient there. So put 1 in all of this. 1 to the power of negative 2 is 1 over 1 squared, which is just 1, or minus 1, sorry. And then minus 2 times 1 is minus 2. So I rewrote that over there so you can see what's happening. It is still minus because the negative power becomes 1 over 1 squared, but then minus all of that, which is 1, is minus 1. So minus 1 minus 2 becomes minus 3. So the gradient at the tangent line to the point 1, 0 is minus 3. Last example, example 5, show that the derivative of the function 1 over x to the power 5 is always negative. So what is it asking for? That the gradient is always negative. How do we do that? Well, we know how to find a gradient, so let's start with what we know. So 1 over x to the power 5 can be written as x to the negative 5. And the gradient of that is simply bringing negative 5 to the front, so negative 5, and then minus 1 from the power becomes minus 6. And we can rewrite that as minus 5 over x to the power of 6. Now we can see that doesn't matter what x is, so if x is positive, positive to the power of 6 is positive, and then the minus in front will make it minus. And then if x is negative, negative to the power of 6 will always be positive as well. So the minus in front of a positive is also minus. But how do we write that? So we say since x to the power of 6 is positive for all x values, where x is not 0, then we have that gradient f dash x is always negative, so less than 0, for all x values, where x is not equal to 0. Okay, thank you for watching. Retry this example to make sure that you have the explanation bit down pat. So cover it or rewind and pause and try and do this and see if you've written the same statements. Thank you for watching, and I'll see you next time. Bye!